Start recording. Okay, so we didn't miss much. We just missed a little review on the recording. Only missed about a minute or so. In case you're looking at it, I'm just writing the position vector, which is written down, to show that we want to find the velocity vector. So, yeah. Not having a little bit of a hard time getting going this morning. So, the velocity vector is going to be equal to dr dt. Now, this could look confusing, but it's pretty simple. Let's go and look at, let's look at how to do it and see what we'll come up with. We're going to sort of slide forward a little bit. And for an instantaneous velocity, right, or to take the derivative, we can just take the derivative of each component. It's just like Calc 1. So again, here's the Chapter 2 part, right, which gives you Vx, and you just take the derivative of the other components. And where we ended last time, because we did the circle, I remember we did that, but we wanted to look for this velocity vector at t equals 15 seconds. So what we want to be able to do is go back and, because like I told you guys, I don't remember anything, so I can't remember what this is. So I'm going to write it on a pen. You can just take the derivative of each of these polynomials. Alright, so let me see here. I need a regular pen so I can keep track of everything. There we go. So we've got negative 0.062t plus 7.2 0.44t minus 9.1. Okay, so if you take the derivative there, I took those pretty quickly. The polynomial derivatives shouldn't be too much of a problem. If we look here, we'll get that Vx, hold on, Vx is equal to negative 0.62, and I know everyone likes a zero there, negative 0.62 t plus 7.2, and then we have Vy equals negative, or no, not negative, sorry. And that's going to equal 0.44 t minus 9.1. So it's not, the handwriting's not super clear. Let's say a minus sign there. But you can see you have these functions of t, right? And you can just plug 15 seconds in, and you can get your velocity components, which if you do that very quickly, let's see what you get. Someone plug it in and see what you get. All right, so negative 2.1 in the x direction or the y direction? Okay, so that'll be, so let's write it here. The velocity vector equal minus 2.1 I hat, and what'd you get for y? A minus 2.5 for y? .5 j hat. you have it. You have your velocity vector. All right, so that wasn't too bad, right? I mean, does everyone see the process? Good, good, good. Okay, so moving forward, we can see that the velocity vector is tangent to the curve that the bunny goes on. If you look at it, you can make it tangent to the curve. And I want to remind all of you that we can see that the vector, the velocity vector, does not start from the origin. It's just tangent along the curve. So you'll notice it points towards the third quadrant, right, at this point. It has those values. You just sort of pick up this velocity vector and you put it right there. All right? And you'll notice we have negative and negative, so it points to quadrant 3. Everything should make sense here. So if anything doesn't make sense, this is a good point to ask questions. I'll kind of try and review it. You take the, you go back here. All right. Here's where we start. No, that's not where we start. Here's where we start. We take the derivative, so we have position vectors. We take the derivative of these two components. This is our x and y components. Once we have those derivatives, we have our new equations. All right, which were in the previous slide. And then we plug our time, 15 seconds, into both of those. We get a new vector. And once we have that new vector, we're good. Okay? So once we have that new vector, that gives us our velocity vector. We calculate it to be negative 2.1 in the x-hat direction. So we calculated v. I'll write it again. Negative 2.1 in the i-hat direction, minus 2.5 in the j-hat direction. And of course, this is a velocity, so we want to put meters per second. We don't want to forget the units. Don't want to get too sloppy. And we can put those in a parenthesis if you'd like. Okay. All right. So now, hopefully, you should be able to predict the next topic. If we've done position, if we've done velocity, we should, there we go. We should now move on to acceleration, right? So, if you remember the flow of Chapter 2, we define these quantities in general, and then we look at specific cases. And Chapter 4 is going to go the same way, almost the same specific case. So you'll notice the math is very similar, right? A average is equal to, let me go to my pointer here, is equal to delta V over delta T. A is equal to dV dt, right? And we can write this in unit vector form. A is equal to dV dt, ddt v, vx, vy, vz, and you get a derivative in each component. So the derivative just works the same way it does in Calc 1. No issue here. And I'm trying to think and see if I have anything else to say about it. I hope again you're noticing that we have the same procedure just applied again. That's what we're doing. Okay? So you'll notice that you have here, they just recast those derivatives as the AX component, the AY component, and the AZ component. Okay? So let's just practice a little bit with general acceleration. So you'll notice you have 4 descriptions of the position in meters here of a puck as it moves in an XY plane. So you'll notice you have X and Y components for one. And you'll notice it says x and y, or you'll notice in 3 and 4 it just gives you the I and j components. It's the same thing. So it wants to know are x and y accelerations constant components, and is acceleration a constant. So these kind of build up on each other, right? In order for a to be constant, both the x and y acceleration components must be constant. So let's go and look at y, or 1, and they'll have you work on the other 3 or 4 on your own for a little bit. I'm going to resize this. There we go. Now it's not so strange on my screen. Okay. So I will do this with pen first, and then I'll have you work it out. So if we look at x, right, we want to know about a. So we have the x component. We want to look at a. So I'm looking at 1. So first I'll figure out what dx dy is, and then I'll figure out what the second derivative is. I didn't say this first part correctly. Hold on. So this is dx dt. All right. And we can see here that the first derivative will be minus 6 plus 4. This is t. And the second derivative, very simply, is minus 6. Right? So ax is going to equal minus 6. All right? And we can see similarly ay will equal 12. See if you can do that. So this is the procedure for 1. Right? Take the second derivative. I found it here. And for 1, a is equal to minus 6i plus 12j. These are both constant, right? So the acceleration is constant. So take a minute and work on 2 and then 3 and 4, and see if you can figure out. We'll make a little thing here. So we'll put here a little table. Right? So 1, we have yes, yes, and then yes. Right? So we'll do that for 2, 3, and 4. So what? Huh?
How do you know it's a constant?
Well, you have to take the derivative, right? You got to take this derivative here. So let's look again at the procedures. So the question is this constant? X is this constant acceleration. So you take the first derivative for velocity of x, right? So that first derivative is going to be minus, bring the 2 down, minus 6t plus 4, and that's your first derivative, right? But the question isn't is the velocity constant, is the acceleration constant, right? So with the acceleration, you have to take the derivative again. And you'll notice here, the t goes away, right? So if the t goes away, it's constant. So ay is minus 6, and for the y component, so the x component is constant. You'll notice again here, if you just take the second derivative of this polynomial, you get 12 because the t disappears. Now, if you have a t left in your acceleration, it's not constant, right? So basically, if you have a situation where a of t, right, equals, I don't know, say for argument it equaled 5t. That would not be a constant acceleration, right? You just have a number here. So And in order for the total acceleration for the vector to be constant, you need to have both the x and the y components have constant acceleration. Okay? So in 2, let's work through that one together before we work through 3. So 2, you'll notice, has a third-degree polynomial. If you take the second derivative, you're still going to have a function of t here. So for 2, the x component is definitely a no. All right? And again, with enough calculus, you can see that if you take 2 derivatives, this term disappears, and this one is a function of t, right? Because it has a third-dimensional polynomial. So you could say yes for y, right? But then no here, because in order for this to be a yes, both of these have to be yes. Okay? Does that make sense? So try to work out 3 and 4 on your own and see what you come up with. It looks like we might be struggling with this one. Is everyone okay? So, look really closely at 3. Take those 2 derivatives. All right. Just remember, if you want, you can. They're all polynomials, so we can look at the highest degree of the polynomial. So, like, if it's squared, or if it's 2, if it's greater than 2, you won't have a constant derivative. If it's 2 or below, you'll have a constant or constant acceleration. Yes, the I-hat. So that is a very good point, Zilla. When you take derivatives of vectors, you just take the derivative of each component, and it's you can consider it like adding. The I-hats and the J-hats stay. The derivative of a vector is always another vector. All right. So you only take it component at a time, and you keep the components. Okay. All right. So I have one. So for 3, let's take a look at 3. There seems to be some confusion here. So let's take a look at 3. If we look at each component, right, the second derivative of this one is 4, right? Does everyone see that? And the second derivative of this part is going to be 0. So V, for this particular problem, for 3, V is just going to equal 4 I hat. Basically, it only has velocity in the x direction. So this one, so for 3, I'm going to say yes, yes, and yes. 0 is a constant. All right. If you're at 0, you're not changing. You're not changing. Okay. So does everyone see why 3 will be yes, yes, yes? Good. Now with 4, you'll notice you have a degree of your polynomial is 3. So we can just by inspection, once you should have this calculus, you should have calculus mastered to the point that by inspection you should know that the second derivative will result in a t term to the first dimension. All right? So this is definitely no for 4. So we know automatically then that the total is no. Now we just have to look at this part. The derivative of a constant is always 0. So this will be yes. Okay? So hopefully that makes sense. I'll leave it up there so that the video can be paused and looked at. But let's move forward. We can see that we got the checkpoint correct. And we now want to apply our, if we remember, we want to apply our acceleration vectors to our rabbit, negative 0.62 t plus 7.2. And that's going to be Vx. Over 4t minus 9 point something, 0.1. All right. Okay. Now, looking at this, Vx, Vy, we just take the derivative again. So it should be pretty simple. So we're going to see that process again to get A. Remember, A equals dv dt. I just want you to see this as many times as you can. And so that means that A of x equals minus 0.62, and A of y equals 0.44. I just simply took the derivative of those linear functions up above, and that's all I did. And we can see that our A vector, no, why did I do that, comma? We can see that A equals negative 0.62 I hat plus 0.44 j hat. Okay? And of course, this is an acceleration, so we need to be careful and get our our act together. And we have the acceleration vector. All right? So I want to go down to the rabbit. We're going to look at the picture again. Oh, no. And you'll notice with the acceleration vector is pointed, it's constant, and it will always point this way. So I'm going to do something. I'm going to try and make a point here in a way that I think is interesting. I want to draw the acceleration. No, not a text. I want to draw a line. I want to show you what I mean by the acceleration vector is constant. So I'm going to draw a line. And you might be wondering, well, we already know that acceleration vector is there, right? But I can move this acceleration vector will stay the same Hold on, this might be easier with the mouse actually. Oh yeah. So it will stay the same no matter where you are on the curve, whether you're at t equals 0 right? If you're at this position, the acceleration vector points in that direction. It stays the same as we move throughout the curve, right, until we get to our point at 15 seconds. And then as we go forward, it remains the same. All right, so that's one thing I wanted to point out. The next thing I wanted to point out is that our position vector, this is probably the only time you'll see me do something like this, but I want you to notice that the position vector, which we can start from the origin, but pick it up and move it here, looks different, and we'll make another, hold on, let's call that the R vector, and then let's pick a different color, and remember the velocity vector looks different. You will very rarely draw all of these at the same time, all right, because as you'll notice, they point in wildly different directions with a lot of dimensionality. Now, sometimes, if we're lucky, we'll be able to have things look very easy, but we'll have to know why they look easy. It's not enough to just assume something goes in the same direction, or that because you're moving in a direction, you're accelerating in that direction, right? You know, you have to look at the whole picture. And you'll notice here you have these three vectors, right, that are going in very different directions. Now, much like we did last time, what I mean by that, much like we did for Chapter 2, we looked at, we went from our general description to specific cases. And I want to point that out again, because it can be tempting to think that when we talked about free fall kinematics or constant acceleration kinematics, that's the answer. That's always what acceleration in VR. And I just see this time and time again on exams. You always have to make that step and think about that and go, is this constant? Right? If the acceleration is constant, then you can apply these constant acceleration kinematics. If it's not, you can't. You have to derive from the general expressions your own velocity and position expressions. Okay? So keep that in mind again as we now go to projectile motion, which is a constant acceleration process. All right? So in projectile motion, all right, so projectile motion is sort of what you think it is. I'll move back for a minute. And you can, it's basically anything you can launch, right? I'm going to try and catch it, but I'm not nearly as coordinated as I like to think I am. And again, we only care about a projectile once it leaves my actual hand. We don't care about the projectile beforehand, what my hand is doing or anything. It only matters once it leaves the hand. All right? All that complex stuff, much like in Chapter 2 in free fall, can be encapsulated in the initial velocity. All right? So projectile motion is a particle moving in the vertical plane with some initial velocity whose acceleration is always free fall acceleration. So the way to look at this is that the acceleration, so we know when we construct the acceleration that AY will be equal to minus G J hat, right? Just like in free fall. And that's it. Now, what do you think AX is going to be equal to? This is the tricky one. Good. AX will be equal to 0. If you don't believe me, I challenge you to identify what would be causing the acceleration in the x direction. Now, we are going to neglect air resistance. Oh, you guys having a hard time hearing me? So the sound might be scratchy for a mic feedback. My mic is about 10 years old, and I'll try to talk a little softer. Okay. So tell me when it's, if I talk a little lower, is this better? Okay. I will try to teach a little lower, but it's not my usual teaching voice, so it's going to be very weird for me. But this whole experience is weird for everybody. So let's give it a try. I'm used to talking in my classroom voice, and having you all there, I kind of get into it. Okay, so I will make my voice lower. If I mumble, let me know. Someone might need to chime in on the microphone and let me know if I mumble, because that could be bad. So x in the x direction, a is 0. Oh, hey. I don't know why I just selected everything, but ay is 0. And again, like I was saying, if you don't see why that's the case, simply ask yourself what would be causing the acceleration in that direction. Okay? And again, we're going to be neglecting air resistance, because for large objects, air resistance doesn't really matter all that much. And you know, we'll see what's doing, what's going on. Okay? I want to select this here, though. I want to deselect this. This is distracting. Hold on. Maybe if I clear all. Okay. So then when doing this, we can see that, hold on. I don't know why it has this hand thing. We can say that A equals 0I minus G J hat. Okay? So for projectile motion, we're always going to have this acceleration. Okay? Now, the motion, if we have an initial velocity, right, that velocity is going to have both an x and a y component. And remember, this is the initial velocity, not the final velocity. The final velocity will often have to be solved for. So you'll notice that since we break these into regular components, we have that v naught x equals, or v naught cosine theta initial, and v naught y equals v naught sine theta initial. And sometimes these things will be 0, so you have to be careful. When are they 0, when are they not 0? And I want to point out to you that we're coming up with a procedure, right? It will be up to you to sort of interpret the physical problem and plug in the correct values, okay? And this star is very important to read. In projectile motion, the horizontal motion and the vertical motion are independent of each other. That is, neither motion affects the other. In fact, there's only one quantity that you can use to relate the x and the y motion. Does anyone want to take a guess what that is? I'll give you a hint. It starts with a T and rhymes with mime. Good. Yes, very good. Time. 5 seconds in the x direction is still 5 seconds in the y direction. Okay? So, well, talking lower may save my voice too. So there's a unexpected benefit. I went from a... This is odd. Okay. No, I'm just looking at my cursors. It is what it is. So we can compose the motion, both the position, the velocity, and the acceleration to those two components. All right? So we can look at the vertical component and treat it as a Chapter 2 freefall problem. And then we have this new horizontal component, all right, to the motion. So when you do a problem in projectile motion, you're really going to want to break it down into two and sort of have your x stuff and your y stuff here. It's a little bit like the green car, red car problem, which I hope you've all suffered through vigorously. In the few of you that asked for help on that problem, I recommended strongly that you make a red car table and a green car table to keep just everything straight. You want to do the same thing with projectile motion. So let's look at this checkpoint here, all right? And we'll see if we can use our table above. So at a certain instant, a flyball velocity, so at some instant, has a velocity of 25I minus 4.9J. Remember, this is in meters per second. The x-axis is horizontal, the y-axis is upward, and v is in meters per second. So it wants to know, has the ball passed its highest point? Okay. Well, let's take a look at the velocity vector first. So the velocity vector is a little bit, if we look at it, it has positive x and minus y, or let's make a little coordinate system. Hold on. That is, the coordinate system is trying to fight me in ways I don't appreciate. So yeah, if you need me to speak louder, just someone chime in and say louder, so that way I know. Or softer. You guys can vote for someone to do that, or just chime in. So let's make a coordinate axis. Now, if we look here, you'll notice that we have a positive x component, right? So here, and the y component is negative. So this will be the quadrant, positive x, negative y, so we'll be in this quadrant. Okay, so let's draw that. We know it'll look something like this because 25 is a lot bigger than 9. So that being said, if we look, the question is, has the ball passed its highest point? This is a great physics problem, right? Because you have to read the math to interpret it, but you're not necessarily have to solve anything. So a projectile motion problem looks like this. So let's break it up into regions, right? Let's do the highest point, and let's notice some things. So we have our initial point, right? Our top point, and our final point. And I want you to notice that projectile motion will always look like a parabola. You should sort of be able to see that because, remember, the acceleration vector, right, ax equals 0, and yx, or ay rather, minus g. Okay? So, I have this parabolic arc. So, what should the vector look like? What should the velocity vector look like at the top? Let's ask that question first. So remember, the velocity vector is tangent to the curve. So what does the velocity vector look like at the top? You try working it on your own. See what you get. And remember, I'm asking what it looks like, not what it's equal to. So all you have to do, good. So all you have to do is, we'll change colors here for velocity vectors, is find the top. And you notice, and you draw your tangent vector. And you'll notice that that tangent vector is horizontal. So if you're at the top, what should be your value of your j component at that instant for the velocity? 0. Good. So we're not at the top, right? But we'll notice something, so now we have to look and see if we're before and after. So if I'm in the before part, let's look at some points here. Let's do some points after. The vectors aren't great because the stylus isn't great, but the general idea should come in here. So look at the x component. The x component, you'll notice, is always, the x component is always positive, right, as we go through. On this side, though, the j component is always positive as well, wherever you are. You'll notice it's actually, you have to be careful there, Mina. If you notice, we're actually slowing down. So the number is the slope is decreasing, right? The position is increasing, but the velocity is in the y component is slowing down. And then we get to 0 at the top. But you'll notice that even though it's decreasing, it's still positive. And if you look here, is the slope of the y component, not the x component, is it negative or positive? Always on this side. Right. It's negative. But we have to be careful between talking about the x values, the velocity values, and the acceleration values. Because even though the x value is increasing, the x value increases throughout the whole problem, right? But the y value will increase, and then it will decrease. Okay, remember, what's important here is that these two, the two notions for the x and y components are independent of each other, right? The only thing that we can translate between one or the other is time. Okay, so if you look here, I think Brandon and David pointed out it's negative. A few of you got there. The velocity value will just keep getting more and more negative, of course, until it hits here, and then yeah, it'll keep going down, right? So now I think if we can ask this question in a different way, right? We can ask, has the ball passed its highest point? So, well, the real way to ask that question is the j component of our velocity positive or negative? Well, is it positive or negative? It's negative, right? So if it's negative, that means we must have passed our highest point. Okay? Pretty simple. So does that make sense to everybody? Let me know. Chime in. Yeah? Okay. Yeah, I can repeat it. So, if you look here, the question, has the ball passed its highest point, can be reinterpreted to what is the sign of the velocity vector? All right? Actually, I'm going to do this with my pencil because this might be more fun. So what is the sign of the y component of my velocity vector, which is this one here, right? And you'll notice that it's negative. So looking at my picture, right, I can ask, well, where is the vector? Where does this vector negative in the y direction? The y direction is positive as we rise, and you'll notice you'll get to the high point where the y component is 0, and then it is only after it reaches its highest point does the y component become negative. So because it's negative, we therefore must be past the highest point. Therefore, it is past the highest point and falling. Okay? I'll let you guys look at that. All right. So Yep, no problem. Life without cough drops is a difficult one. I'll have to remedy that after class. So when we look at this here, you're going to notice with projectile motion, we have our vertical motion, right? And we're going to then also have our horizontal motion. So vertical motion, you'll notice this is chapter 2, plus our horizontal motion, and that will give us this projectile motion, and you can see the arc that's created here. So here's your velocity, initial velocity, and then you'll notice that they have the Vy equals 0 at the top, and you can see this is the rising part. But you'll notice that this looks just like chapter 2, right? This vertical part. And now we're just adding this horizontal constant or 0 acceleration part. Okay? So I don't think it does this in a way I like. Let's see here. Oh, good. Actually, I do like this. So this gets us to the top, right? And you can see with the horizontal motion, we get to the top. The vertical motion has just gone like this, right? Started, keeps going, keeps going. Now we'll look at the descent. Okay, so starting up here, again, you'll notice this is the second half of a free fall problem, but you'll notice that the horizontal motion just keeps going. All right, and this gives you the full arc of the trajectory. And you can notice that you see the same thing with V here. Vx is positive, Vy is negative. Just in case my my drawings and doodles were not helpful. This should be a little more helpful. Okay, so take a look at that, and that should make the checkpoint make a little bit more sense. So I think that's what I show there, is that that's, yes, the negative ball is negative and falling. Okay, so now we have our equations. So let's look at what's going on. So since we can break things into x and y motion, remember ax equals 0. So therefore, x naught delta x, which we have here, is going to be equal to v naught xt. And remember, these are vectors and components, so you'll have it as x minus x naught, or delta x, equals v naught cosine theta naught t. All right? So you'll notice the x equations are pretty simple, pretty straightforward. And the y equations just look like our chapter 2 equations, right? But instead of calling it delta x, we'll pretty much, I think we always called it y before, but we'll pretty much formally always call it delta y. I think the part that might be the most confusing is you will have an x component to the velocity and you will have a y component to the velocity. You don't want to get those mixed up. All right? Now, you can actually, if you look at this equation, it's actually the same derived from constant acceleration. The full equation, delta x equals v naught xt plus 1/2 ax t squared. So this term still exists in these first sets of equations, but with ax equaling 0, it goes away, and you can see that this is all you have left, and that's what is written here. Okay? And then they're just using the component there. So it's still the same equation you have, and you'll notice you just plug in your minus g for your a, and you get the equation here. And you'll notice that you have, with the constant acceleration that's not equal to 0, you'll have the full set of kinematic equations. So you'll have you will have this equation, right, which is kind of the big one that we can derive right from calculus. But then you can get these two. You can just get, just like you did in chapter 2, You can get these from algebra. Okay? And you can figure those out on your own, but you can always certainly use them if you want to. If you're wondering if we're going to be doing some problems, we will. But I want to get through this. Are there any questions on this? I think this is a good place to take a short break. We've introduced these. We can come back in about 10 or 11 minutes and look at them. Okay? All right. So I'll keep recording and I'll be around. I'm gonna refill my water. So I'm gonna disable my video before I get up. But I'll keep the mic on. Yeah, I think I may have been a victim of the corona fever. I had a fever and everything about not last weekend, but the weekend before, and sadly, I'm respiratory at risk, so I have asthma. So it just means that any cough I have lingers for a while. But I have had worse coughs, and it doesn't burn when I cough, so it's actually sounds worse than it is probably. Because I know dry cough burning. I think not this time, but I think I have scarred my lungs previously, and it takes a long time to recover. So, actually, I pretty much, yeah, I do. And don't worry, I didn't expose you guys. After classes were canceled, it happened to have been my birthday, and I saw some friends of mine who came down with similar symptoms before me, almost right after. So they got the fever and the cough on the Thursday. So I saw them on the 12th after we'd already stopped seeing each other, and then I became symptomatic on Sunday. They became symptomatic on Thursday or Friday. So maybe I don't know. Maybe if I saw you Tuesday, maybe I might have already had it. But it seemed to have followed them pretty much. So it took 3 days since I saw them to start getting sick. So I hope all of you have been okay. You wouldn't have got it from me at this point if you got it. But it's one of those things, it's just going to, they talk about flattening the curve, but they're not really telling people, and I kind of think they should, is that everyone's going to be exposed. It's just about not overwhelming the health system, not really stopping the disease. They call it, social distancing to stop the disease spreading. You can really just slow it spreading. You're not going to stop. And once we get to 1%, that's pretty much the ball game. What I mean by that is everyone will be exposed. That's impossible for it not to happen, and they'll be exposed quickly. If we reach that 1%, we're still exponential. And if you look at the numbers, we're kind of getting there. Right. So if the numbers are as high as 10, probably as high as 10 times and as low as 5 times. So if 1% of the population would be 3 million people. So if you divide that by 10, if we get to 300,000 cases, 300,000 or 600,000, that's when social distancing actually doesn't matter anymore. At least as far as my understanding of disease spreading. Once you get to 1% of the population, you very quickly get to 100%, extremely quickly. Remember that when you do an exponential doubling, an exponential growth, right, the difference between 150% contamination and 100% contamination is the very last step. So it's the very last doubling. So keep that in mind. Exponential growth is scary. I'm going to get my water. Hold on. All right. Oh, I threw a silverware. I'll throw that away. Oh no, it got really dirty too. Oh boy. Wash the dishes. Okay, I'm back. Allow the camera. So, fun story. I actually thought I was teaching Physics 2 before Physics 1. And when no one showed up in the room and class started, I realized my mistake. So, I think someone did that earlier in the week. So, fun times. Oh boy. Making the best of online learning. Okay. So, let's continue on with our with our discussion. Got my water. All right, so we have our equations for constant or for projectile motion. Again, you'll notice that the y equations are more complex than the x equations, but that's okay. All right, so let's go forward, shall we? All right. I hope people are back. Let me see. Good. Yeah, we're all back. Well, Mina's not back, but we're getting back. All right. So now these equations are kind of nice simplifications. They give you a range and a trajectory. All right. So the path through space, the parabola, can be found by eliminating time between the equations in the x and y direction. So you'll notice you have y in terms of x. This is a mathematical result. Often it can be used to make your life easier, but we all know that I'm not the biggest fan of straight up math. I think you do yourself a lot of favors if you develop the equations for each situation. It gives you practice doing that because that's a skill that transfers forward. Memorizing this particular equation and just applying it is not a skill that transfers forward. All right. So yes, if you have, if you want to look at the y as a function of x, you can do that. Like where is it? What's its y value for its given x in position? You can definitely do that. The range, the total x component it will go, is equal to this equation here. But you have to be aware that this range equation really only applies when you start like this and go like this. Most questions will just take a slice of the curve at some point. You can pick whichever ones you like and ask for only a slice of it. So all these can be helpful. And if you recognize that they're the right thing to do right away, that's fine. One thing to keep in, but again, you want to be familiar with what you're talking about. One thing to be very careful about when it comes to projectile motion is context and quantities. I can't tell you how many times in a problem, right, Vx initial may be equal to Vy final, or to Vx final, rather, right? Now, you have to show that you know that this is true because Ax equals 0. And what I mean by this is people will do analysis and they'll get this when the question asks for this, for the initial x. All right? You can't just solve for this and do analysis and then say I'm done. You have to recognize that Ax equals 0. Hold on, let me see if I can. Ax equals 0, and therefore you can make the connection between Vx final and Vx naught. It's getting a little crazy, so I'm going to clear everything. But but again, you want to be careful. All right, you have to get to the correct final quantity. So use these equations sparingly. In the calculations, we assume air resistance is negligible. This can be a not bad calculation, but sometimes it can be a poor, and often the longer we have a problem go, it can be a poor approximation. So without air resistance, which is what we'll mostly do, you'll get this nice long range. But you'll notice that the air resistance will both reduce the height and the range. Now, it's not hard to get a modified to include air resistance, but it requires Chapter 5 knowledge and Chapter 6, or Chapter 6 knowledge, really. So we have to get there before we can sort of come back and add an air resistance, which will modify the acceleration, and therefore, affect our problem, and then we can get the correct curve. But you'll notice it's still a parabola. So what that means is it's still going to look the same. Nothing will change fundamentally, but the numbers will be off. You'll find with lab that you can play with the air resistance quite a bit and see how it affects things. But sometimes it's not a terrible approximation. But as your time goes on, as your process gets longer, or is spinning or moving, it starts to become less and less useful. So let's go forward. All right, so let's do this checkpoint, and let's talk about it. So we have a fly ball is hit into the outfield just like before, but you're going to notice we're going to ignore air resistance, right? So we want to look at what happens to its horizontal and vertical components of the velocity, and what are the horizontal and vertical components of its acceleration during ascent, during descent, and at the topmost point of its flight. Okay, this is one of those word vomit checkpoints that has a lot of words. So let's sort of recast the question in terms of something that makes sense. So we're just going to do A and B, velocity first, and then we'll do acceleration. So I think how I would write this up is I'd say, okay, so we want happens to its, we want to be clear, horizontal components of velocity, that question mark, what happens to its velocity during what conditions, right? And then C and D are the acceleration, and then now we have this during. So we want to know what happens to its horizontal and vertical components of its velocity during ascent, descent, and at the top point of its flight. Okay? So we've already looked at a trajectory before. We know that the pop fly ball is going to look something like this. And we've already sort of looked at velocity already, right? The horizontal and vertical components. So we know, so we'll actually do part B first, right? So, so B, during the ascent, we will increase, stop, and then we will decrease during the descent, right, and become the most negative. So we have that. Oh, sorry, you can't see that part. We have this part where we go up, up, down, and then, and at the topmost point of the flight here, we start descending. We start decreasing. So, but now let's go to A. So A, you'll notice with part A, the horizontal velocity, since AX is 0, because it's projectile motion, right? This should remain unchanged throughout the entire process. And if you remember our previous breakdown of vertical and horizontal components, it showed that quite clearly. So we expect A to be unchanged, and the velocity will go from, well, actually, always, if you look at it from a number line perspective, right, you'll start with some velocity here and decrease through the whole thing, right? So if this is 0, you have some initial velocity, you slow to 0, and then you start going negative as you go as you go up here. Actually, AY doesn't change. Only AY is not 0. That's the key part to remember. AY is negative G, AX is 0. So it's only VY that changes. VX will be constant. You gotta be, remember I told you you might confuse acceleration and velocity, and that can happen. It can happen quicker than you think. I do it frequently. It's a big deal though when you're taking a test or an exam. I, of course, just get to erase the report and go, oops. But you want to be careful, and you want to try and recognize when you mixed it up. That's the important part. So, so keep in mind what's changing. So because AX is equal to 0, V is not changing in the X direction. So for A, it's going to be constant. Part A, Vx is constant. But for part B here, you'll notice that you start with some velocity, and that velocity gets gets smaller and smaller and smaller, and then it becomes 0, right? But you'll notice we now go negative. We don't go back, we don't accelerate and fly up into the air. So you can actually say this is decreasing or becoming more negative. All right? Now what I want you to do is consider the vertical components of y. So we actually, in looking at this, have answered C, right? So during the entire process, ax equals 0. So what is ay equal to the whole time as we go up and down? I'll give you a hint. It's only one thing. Right. Well, negative 9.8 meters per second. All right? So when we go, you'll notice that if you draw the acceleration vector, which I should have done in a different color, it always points down and is always minus g through the whole process. Okay? And to go back to, whose point was it? To Tala's point about what's changing and not changing, the acceleration does not change, but the velocity does change. Okay? So, and because the acceleration is pointing down, remember, you start with this initial velocity. The initial velocity decreases, 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 and then it gets to 0, right? Here we're at the top. And now we've changed direction. We're no longer going up. We start falling down. And that increases, 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 increases. So when you're reading these problems, you're going to hear things like, just as you leave the hand, right? And as you leave the hand, this is where VO comes. Everything that happened to get it up to that velocity is encapsulated by V naught. All right? However, these problems end just before you hit the ground. After you hit the ground, you're no longer in projectile motion. Other stuff is happening. The problem gets hard. Okay? So does that make sense? Does the checkpoint make sense? Everyone have any questions about the what we did here? Everyone feels good with all those answers? All right. Okay. So moving on from our checkpoint, we will now have our example. All right. Oh, right. We have the answers, so you can check that everything makes sense. So we have a rescue plane that flies at 190 kilometers an hour, or 55 meters per second. I'm very happy the problem did that for me. And it has a constant height of 500 meters towards a point directly below a rescue victim, a victim who needs to be rescued. So we want to know what should be the angle of the pilot's line of sight to the victim when the capsule's release is made. So the first thing you want to do here is draw a picture. So take a minute and draw a picture. All right? I'm just going to give you about 30 seconds to write it and see if you can come up with the right picture. All right. Okay. So now let's look at the picture. Is this kind of what you came up with? Good. If not, take a look at it a little bit and try and get there. You'll notice you were given, let's try and draw some of the given stuff. So we have H equal to 500 meters, right? We have V naught equals 55 meters per second. And that's it. And then we have, they want to know what this angle phi is, right? So how are we going to do this? How are we going to do this? Well, it's tempting to hunt and peck. That's what old thing for typing when you do hunt and you look for the, peck the thing. It's tempting to hunt for an equation, but we'll have to sort of recognize when we can use our projectile motion equations or our when math is just going to help us get what we want. So usually what I try and do is I'll look at the math of what I want and then go forward and go back. So you'll notice up here when I'm writing here, we have that tan theta or tan phi rather is going to equal, right, the opposite over the adjacent. So let's look here. The opposite is delta x over h. That's just from the triangle, right? So I have I have h, I want phi, and I need to look at delta x. Now things might become useful, right? So when I look here, this delta x will be equal to 500 meters. That's given. So I have that written. I have that written at the top here. H is equal to 500 meters. So now I can look here and say, I want delta x. Well, delta x, we know, is going to be equal to v naught t. And I'm just going to write that because two other things that were given. So I want to sort of stop here to take a break. Not leaving a break, but from just powering through the problem, which I can do sometimes. But I want to stop here to point out some things. One, if you look at the problem, if you go back to the problem, I don't want to delete everything, but if you go back, you'll notice that the accelerations are not given, they're implicitly given. So it's safe to assume that we are on Earth, right? So if that's true, we can write down that ax equals 0, and so there we'll be done with this term for delta x, and we know that ay will be equal to minus g. We can always assume those things, and they won't always be explicitly given. So you have to understand the context of the problem you're solving. And because we know that, we can move forward. Because even though we don't have t, we'll be able to use our y equation to do that, which I'll do in just a second. But I want to point out some things. One, if you look at the picture, notice that phi is not equal to theta. These are two different angles. And also notice that your v naught here is not the same as your final velocity. Your x component will be unchanged. This is true, but you're going to have a y component. And if you want to, for instance, get the angle of this theta at the end, or the final velocity, you'll have to consider both components in the vector. I think that's part B, but let's deal with part A first. So you'll notice going through here, again, setting up the problem, I want phi, so I wrote an equation that has phi in it, so I know what I can solve, but I don't have delta x. So now I wrote an equation down for delta x. I do have v naught, right? And notice the initial angle for v naught is 0. So we can write up here that theta naught equals 0, right? So we can just use that number. I guess if I want to be really equals v naught t. But now I'm still in the same predicament. I don't know t. But because I have a projectile motion problem, I do know that delta y, I can use my other dimension to get t. That delta y equals v naught y. Hold on. Nope, 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 nope. V naught y t minus 1/2 g t squared. Okay, few things to note here. Delta y starts at the plane, right? So your displacement, because you're going down, you want to be consistent, is not going to be 500 meters, but it's going to be your final position, or right? It's always final minus initial. So your final position. Wait a minute. Yeah, final minus initial. So it should be no, because we should get negative 500 here because we're going down. So usually we'd start here, right? So if I was up here, it would be final minus initial. So our final is going to be minus 500 minus our initial is 0. Yeah. So we're starting here and going here. If you wanted to do positive 500 would be way up here, right? But negative 500 is down here. So, so pick your position, right? If we call this the origin, the plane the origin, right here would be minus 500, not 500 if you're making a coordinate axis. So we're going to notice that delta y will be negative. That's going to be important. But remember what we said earlier, that V naught is perfectly horizontal, right? I'm pointing down right here. That's perfectly horizontal, which means that V naught, hold on, pushing too many buttons here. V naught y is equal to V naught sine theta naught. Sine of 0 is 0, so that's going to equal 0. And we have delta y is equal to minus h, and that's going to equal minus 1/2 g t squared. The minuses go away, and you get that h equals 1/2 g t squared. Now this is kind of exciting because now we don't have another unknown. We can just solve for t equals 2h over g to the 1/2 power, or the square root, whether you like it. But now you'll notice we have t in terms of stuff we know. So we can plug t, that gives us a number, so solve for t. If you want, and we can see here that delta x will equal V naught times 2h over g. I hope I did the algebra right. Yeah, I did. Okay. Yeah. Okay. This will equal delta x, right? And then once we have delta x, we can plug, now we have a number here, and now we can plug this delta x back into here, into our top equation, and solve for phi. All right? By taking the arctangent. So we can write down here, if you want to see it symbolically, that phi equals I don't do the tan of -1 anymore because I'm trying to make that be the inverse, but that's the button you would look for. So I'm just going to write it out, arctangent of delta x, which is v naught times 2h Why do I write it like this? I write it like this because now you know phi for every iteration of this problem, right? This is a general answer. You can plug it into your heart's content to see what the actual answer or the number is for these particular sets of numbers that we have up here. But you could have a height of 5 kilometers. Maybe it's a different plane. And then if you have that height of 5 kilometers, or maybe you have a different speed in your plane. Maybe your plane coasts at a different speed due to different conditions. You can adjust your angle automatically. All right, and you've solved a class of problems. No, delta x is, oh, I don't know, delta x might be. That sounds reasonable. I think I remember it, but again, I'll leave the numbers for you. I don't really, they're not really my focus if they don't have to be. And I do want to get you used to solving some of these problems, like the symbolic problems that you'll have online. So that's a much more powerful solution than the numbers. When you put the numbers in, you've only solved one problem. When you have a symbolic solution like the one here, you've solved a whole class of problems. So that's how I look at it. So I don't put them into check. I'll let you guys do that and get the experience sort of massaging it yourselves. And the question, because really the question there becomes, did I put it in my calculator correctly? This is the correct answer, right? This is fine. If you put all the numbers in, then it should be, yeah. But if people start disagreeing, then you probably have to get together and check, double check, and triple check your calculations. Okay, so let's get to the next part of this problem, unless there's any questions on this part. Everyone good here? Okay. All right. So, good. Okay, let's go forward. So now it wants to know that as the capsule reaches the water, what is its final velocity? So this is interesting. So we want to know, so we know we have V naught. Hold on. We have V naught equals 55. H equals 500 meters, and we got phi, delta x, and t from part A. These come from part A. So, when we look at this, we know that V naught equals v naught I plus 0j. And of course, we know ax equals 0. We know ay equals minus g. So we know that for v final, right? We know for v final that the acceleration didn't change because ax is equal to 0. So we have the first part there. But now we have to find this final. Now we have plus question mark j hat. And that's what we want to find, is that question mark. Okay? So let's see if we can. The first thing I usually try is to see if the simple equation v equals v naught plus at will work. That looks like that's going to be just fine here. So remember v naught y, so this is in the y direction, right? That did not look like a y. I'm just going to delete that. It's taking more time than it's worth. Okay. Vy is going to equal v naught in the y direction plus ayt. So because we're doing a projectile motion problem, and we know that theta naught equals 0, right? We can see that this reduces to Vy, right, equals minus g times t, right? And we can just, we have t from part A, so we can just plug it in and do the multiplication, and we can see that v equals v naught, our final v, I hat, minus gt, j hat. So part B wasn't so bad, right? And again, with t, you just gotta, remember what we had last time, which you can. I will refer you in the recording to do that, to see what we got. Okay, so that should be pretty straightforward, and that is how you solve projectile motion problems. Most projectile motion problems are a play on what we just did, so you should be able to look at them and see them and have very little issue with them. Okay, so now we want to change gears a little bit to uniform circular motion. All right, so uniform circular motion is going to have some hallmarks of what we've done. It's going to be a constant acceleration type problem, but it is going to look a little different, and we'll have some new terms to define. Okay, so you'll notice, so with uniform circular motion, the particle must go around in a circle. I want you to notice a few things. The acceleration, it's constant acceleration. The magnitude of the acceleration never changes, and the direction looks like it constantly changes unless we turn our heads into polar coordinates. So in terms of polar coordinates, we're always facing towards the center of the circle, and in this sense, oh wait a minute, no, we're not going to do polar. I keep forgetting. R hats and theta hats are difficult. Acceleration is always pointing to the center. So in that sense, it could seem like it's the same direction, but in a rectangular coordinate system, obviously, the acceleration is always changing direction, but not magnitude. So I guess you can see here that we're always going to sort of say that we're going to sort of be able to kind of cheat and say that the acceleration is always pointing towards the center, and has the same magnitude. So it's sort of be able to treat it as constant acceleration, even though it's changing direction. All right. The velocity, you'll notice, is also the speed around the circle is the same, but it is constantly changing direction, right? So the speed vector is always in some, or the velocity vector is always in some weird direction. Okay. So our path is circular, and in order to be uniform, that speed must be constant. If you're asking yourself, oh, wait a minute, what happens if it speeds up or slows down? You are no longer in uniform circular motion. Can't use the equation. It's pretty simple. Okay, so I think I have a bigger picture here to look at. Yes, I do. All right, notice again, acceleration always points towards the center of the circle. So again, I want to talk a little bit more about the cheating part of it. So if we look at it in XY coordinates, right? Everything's sort of all over the place. But the way to really look, and XY coordinates is what we'll stick to. If we look at it in terms of R and theta, right? Now theta might be changing, but in the radial direction, we can say that that the acceleration is constant. And that's usually how we'll look at this. We usually put it in the R direction. However, things like R hat and theta hat are hard. We're not doing these. Beyond the scope of the course. Beyond physics 1. Okay? So we're going to do that. And just sort of stick with things in terms of how we can understand them here. Okay? So, going forward, we want to see how to quantify this stuff. So, the acceleration here is called centripetal acceleration, which means center seeking, and it's directed, you notice they say radially inward, they want to be consistent for future things, and A is equal to V squared over R, okay? Now, the period, so this is your constant acceleration. Now, the period is a new term, right? But the period is pretty simple. It's the time it takes for one revolution to go around. This equation can seem like magic, but it's not. We'll derive this in a second. But you all are familiar with this. What is the period of the Earth revolving around the sun? Does anyone know? Oh, sorry. Here it comes again. Does anyone know the period of the Earth around the sun? Days, or what? How do we do it more commonly? Right. 1 year, 365.25 days. Good. Yeah, that's the period. So, so you have an idea what it is. It's one revolution. If you go around in if we make a circle, and let's move the circle down here. So that's out of the way. We'll move it here. So if we have a circle, and we move around it, I start at the top, and I go around. That's the period, right? The time it takes for that to happen is the period. One revolution. Now, this can seem like it comes from nowhere, but this just comes from the equation that delta x is equal to vt. Pretty simple. And so basically, we look here and we say, well, we're concerned about a particular delta x, which is the period, or the traveling circumference, right? So if you're traveling around the circumference of a circle, it's 2 pi r. You're at a constant velocity as defined by the problem. So that means it takes the period to do that, and you solve for t, and you get that equation. Okay, and so it's all pretty simple. So that's where that comes from. Okay. So moving forward, let's look at a checkpoint for circular motion. So if an object moves at constant speed along a circular path, in a horizontal XY plane, that's good, with the center at the origin, when the object is at -2 meters, its velocity is -4 meters per second. Give the objects A velocity and B acceleration at y equals 2 meters. Okay, well, let's take a look here. Let's draw the problem and in a way that makes this makes this make sense. So we have a circle, right? Before we do that, we should draw some lines. So one line, there's another line. Let's move our circle onto our coordinate axis. That looks pretty good. It's not perfect, but it's pretty good. Okay, so we have our our circle and our axes. Now we want to look at when the object is at -2. We want to read it carefully. So we'll make this a standard coordinate axis. That just means that those are the positive directions. Call this x. We'll call this y. So when x is equal to -2, x is -2. Let's call it that point there. All right. The velocity is -4j. So that means the velocity vector, let's change colors, is -4j, right? And we have -4. So we know if we undergo uniform circular motion, right, we know that v has to remain constant. So you'll notice here that the magnitude of v is equal to 4, right? So, and the acceleration, the magnitude is going to be, at this point, must also stay the same, is going to be v squared over 2, which is equal to 16 over 2, that's a 6, which is equal to 8 meters per second squared. Okay, but now the trick is finding the directions. So let's go to y equals 2. That's here, right? So we have to get this arrow and sort of transport it over to y equals 2. And here we can see at y equals 2, it'll look like this, right? And so we notice that the velocity, yes, Tala. What's your question, Tala? Because that's a good question. So I knew I skipped something. Remember, A, oh no, that's terrible, forget that A. A equals v squared over r, right? So in this circle, if I'm looking at x equals -2, then the radius of the circle, I'm going to pick purple because I can. At x equals -2 for moving in circular motion, the purple thing here is the radius, right? So if I look at my equation, a equals v squared over r, the radius is 2, and that's where the 2 comes from. Does that make sense? No? Well, if the speed is constant, the magnitude of the acceleration does, but you'll notice the direction is changing. So that's where this is counterintuitive, right? So the acceleration, the speed is constant, the velocity is not constant. That's the trick. The velocity, if you're saying if the velocity is constant, then the acceleration has to be 0. Speed is not acceleration. All right? And the velocity here as we move around the circle, is constantly changing. I'll refer you back to our previous slide. I'm going to lose that circle, but notice the velocity is changing. It's changing direction constantly, and therefore there's an acceleration. The absolute velocity is the speed. I wanted to point that out, that we confirmed here that this is the speed, right? So, and that is the absolute value of the velocity. That's the magnitude of the velocity. So in math, you'd say ABS, but here we'd say the magnitude of the velocity, which we write with the absolute value sign. Okay. And getting back to our checkpoint, I'm going to make my circle again. Purple circle this time. I'll make my axes. Move my circle. And again, not perfect. It's not bad, but it's not terrible either. So if we look at the, so let's sort of review some of those things, because we'll probably need to say them again. So let's look at x equals 2, which is right here. All right, so that's the radius of the circle, where I've made the point. This is true. This is true. I can get perfect circles with the writing on the tablet, but sadly I can't be present. But if we look here, this is again the radius. All right, so the velocity, I'm actually going to write that explicitly. The velocity vector is given at that point is equal to minus 4j hat, right? So I'll pick another, but the speed, the magnitude of the velocity vector is going to be equal to 4 meters per second. This is also meters per second. Okay? So that's the difference between the vector and the speed. The speed is not going to change, but the direction is going to change. And let's look at that again in blue. So in our initial point, our velocity is pointing this way, down, minus 4j. But at y equals positive 2, if you transport this arrow and have the, well, no, you can't transport the arrow. If you go around, you'll notice at each point, right, the velocity changes. We're just following around in a circular arc. And this is the point we're interested in, y equals 2. All right? So at y equals 2, right, we can see that the velocity is going to be equal to minus 4 I hat. All right? So you'll notice the velocities are not equal, because this one is in the j hat direction, this one is in the I hat direction, or the final one, the one that we've been asked for. This one's in the j hat, I hat. What I do want to point out, though, is that the speed has remained unchanged. It's still equal to 4. Okay? So, now if we look at the acceleration, that's going to be equal to v squared over r. All right? So v is the speed. Quadrant 1 and 3, well, I'd say on the x-axis, you would be on j hat, and if you're on the y-axis, you would be in I hat. Yeah, because you're not really in 1 or 3. I guess if you took some intermediate value, it would have both x and y components. But as we go here, remember this is speed, v squared over r. So we just take that 4 squared, that's 16, and you can see from the problem here, the radius is 2, right? And then that's what we got before, over 2, 16 divided by 2 equals 8. meters per second squared, and of course, the acceleration vector, which I'll do in yellow, will be pointing towards the center of the circle. No matter where you are, the acceleration vector always points towards the center. And again, our magnitude, it's always in the radial direction, and its value doesn't change. Therefore, it's constant. We can call it constant. Okay? So, questions and thoughts about this? Yes, I will be. I do them via Skype though, because my office hours have to be available for all of the students. Basically, I take them one at a time. You remember, you can always put the origin wherever you want. You know, the origin is not dictated by me or anyone else. You are the dictator of the origin. So always pick origins that make your life easy. That's what I'm trying to say. So no, I would say all of you should probably look for me on Skype. Again, I'll put my email there, and I would say add me on Skype. Let me do at lagcc.cuny.edu. Basically, if I do that, if you look for me there, it's the fish avatar or Dory, depending on how many cartoons you watch. So pick that one. I would say you can text me. That's the easiest way with the messaging. But if you have a specific problem, you can do a video call or audio call, whatever you're comfortable with, and I can try my best to answer your question that way. I feel like that because I'll be able to chat with everybody, I can tell people who are in line. It's the easiest way to sort of manage the most people without being like a 40-minute Zoom meeting or something like that. So I recommend all of you just at least add me on Skype. Skype is free, or add this, and this is my work number, so don't worry, you're not overloading my personal email box or anything. And you know, just it's because it's kind of easy to just manage and chat and you know, for little things, and then video call for big things. So my office hours are going to be the same, but I would encourage you all, I'll always be available. It'll pretty much always be on. See if I'm there, because I stay up pretty late. So if you have a question at like 2 or 3 in the morning and I'm up watching something, well, usually I want that time to myself, to be honest. But up to like, say, 10 p.m. or midnight, I'll probably be around, and you know, we can chat. Okay? I'm trying to be available as much as possible. But I just was realizing as I was saying how late I would be up. I will need time where you know, I'm student free. But that would be, you know, past 10 or 11 or something like that. But yeah, you should be able to find me. I mean, I might be cooking dinner or something, so I might not get back to you, but I'll be checking it regularly. And the computer lets me know if someone texts me on it. So, you know, I get a little notification. So when I see that come up, I'd be like, oh, I should check. And then I'll respond to you specifically, and at least via text. And if I think it needs a call, I'll tell you. Okay? Although today, for instance, I do have to make a work-related call, so I might, you know, like I said, I might be a little bit. But you can text during the office hours, and I can try and get back to you while I do that. And I am going to try and get those cough drops, because I'm going to suffer for the rest of the night if I don't have them. So I might not be back till 4, but I'll, you know, but still ask your questions so I can do it. Oh, geez, I hope Nancy hasn't left. I haven't dismissed everyone yet. We still have stuff to go. So everyone's good here. We only have 5 minutes left, but I want to at least, oh, look, we got that right. I want to at least talk about relative motion. I'm not going to ask you questions on relative motion for the exam, but it's a very important physics topic to talk about. Basically, it's, you know, I want to sort of set us up for it, and we'll talk about it very briefly tomorrow, but then we'll move on to Chapter 5, because that's where more of the meat and potatoes is. But relative motion is important because two observers can see two things, and it's important to reconcile when there can be an easy relationship between them, and when physics applies and when it doesn't. And circular motion is the biggest example of this. But the easiest one to see is I want you to imagine just this thought process, and we'll pick up here tomorrow. But imagine you're sitting in a train, and you're sitting next to me, and I'm throwing the pen up and down, right? So you would describe its path like this: up, down, up, down, up, down. Now imagine you were outside and you saw the train moving by as I threw it up and down. If you're outside, you would see this pattern, right? Up, down, up, down, up, down. So this is from a stationary frame, and this is from a moving frame. And the question always asked is, well, who's right? Which observer has the correct motion? And the answer that Galileo came up with is both. All right? An easy sort of simple numerical example of this is, imagine you have a water balloon cannon, right, that shoots water balloons at 30 miles per hour. Okay? So if you perspectives, I don't like the word perspectives because it's a matter of frame. Because perspectives makes it seem like it's an opinion, or one is right and one is wrong. Here, you can transfer from one frame to another. That's what we're going to see tomorrow. And it's going to, and there's going to be a way to do it, and there are certain criteria in which you can do that, and the laws of physics apply, and certain things that happen that make them not apply. So there's assumptions we can make to make those transfers. So perspectives is a little too general. But going back to my example, if you have a water balloon cannon that fires at 30 miles per hour, right, and you know you fire the can at 30 miles per hour, and you hit me at it, I would say, oh, here comes this water balloon at 30 miles per hour. Now, if you're in a car moving at 20 miles per hour, right, I'll see it, and you fire the water balloon, you'll still see the water balloon because you're in the moving frame as moving towards me at 30 miles per hour. But I'll see it moving at 50 miles per hour because your frame is moving and mine's not. And it's this type of thing that explains why, for instance, if you're in a train, right, and you jump up on the train, the back of the train doesn't come and hit you right in the back. When in fact, hopefully that'll woke you up, when in fact you're moving with the train, so if you jump up, you'll come right back down to the point you were sitting at. Whereas if you're outside the train, right, and you jump up, you will not come down and have the same part of the train be right next to you. So that's interesting because you're not moving with the train. That is the essence of frames. We're not going to go too deep into it, but we will cover it a little bit because I do want to be able to talk about it and for you to have seen it. It's very fundamental physics stuff. It's actually pretty cool, but it applies only marginally to the rest of the course, but it applies greatly to more advanced physics. When I start having physics majors in the course, we'll probably open up this section quite a bit more. Okay, so I think that's it for today. That seems like a good place to stop. I'll sort of stick around for the next couple minutes, but I'm going to turn off the recording now.